This video is about clarifying Homework 9 Problem 3 and our thermodynamic definition of entropy. Some of you described an apparent paradox in Homework 9 in that problem. And I love that you brought this question to me because it helped me realize that there is a very important detail that was not sufficiently highlighted. And now we have the opportunity to bring more clarity and depth to our definition of entropy. Entropy isn't derived, it is defined, but we did do a bit of a derivation to motivate why entropy might be defined as it is. Conceptually, we motivated what we need entropy for in video 4b, and that's an important precursor to this video, and a good sequel is going to be a molecular take on entropy, which answers the question why it is that nature seems to operate in accordance with this strange quantity. But for this video, let's revisit how we defined entropy. And we're going to start like we often do with the first law, solved for heat flow. Regardless of the process I choose to do, I can write that du is Cv dt. And this is the case even for processes that aren't constant volume because internal energy is a state function. And regardless of where my initial and final state are, I can choose an isothermal followed by a constant volume path to get there. We decided to consider a reversible process, and what that lets us do is the work we do for expansion is always pushing against an external atmosphere. But in the reversible case, the external pressure is in quasi-equilibrium with the system pressure. And so assuming reversibility is what lets us write this equation in terms of all state variables, or all system variables. Unlike last time, I'm going to be explicitly clear, though, that we are assuming reversibility by including that as a subscript on the heat flow that we're calculating. Now, I'm going to make the arbitrary decision to divide both sides by T. And just like the first time we defined entropy, what you can notice is that the right side of this equation is composed entirely of state functions. And so just like we did with enthalpy, where we noticed there was a convenient grouping of state functions and we decided, well, maybe we should name that another state function. That's the same thing that's happened here. There is some other state function that is changing differentially on this side of the equation. And this is where our definition for the thermodynamic entropy comes from. Our thermodynamic definition of entropy comes from. The only difference between this derivation and the last derivation was I didn't bother to do the last step where we assumed a perfect gas. We don't have to. These are all state functions, so it's the same motivation. And that I'm being explicit about writing that the change in entropy is equal to the heat flow for a reversible process. And that is the detail that we didn't sufficiently highlight. The consequence of this addition, or this highlighting this detail, plays out in Homework 9 Problem 3, where we talked about irreversible expansion of a piston against zero external pressure. So let's talk about that problem. In this problem, we have a piston and it expands isothermally and irreversibly against a zero external pressure. And the problem asks you to calculate the change in entropy for the system, the surroundings, and the total change of entropy, and to predict whether or not this process is spontaneous. So what is true about this process is it's isothermal, and so the change in internal energy is 0. We're expanding against a 0 external pressure, and so we've done no work. So from these two, and by the first law, we can then conclude that no heat must be transferred. And these are all true. We would then be tempted, though, we might want to say that the change in entropy is equal to 0 because we've got no heat flow. But this is the part, there's where the mistake is. So this is where the apparent contradiction is resolved. We can't conclude anything about entropy from these values because it's an irreversible process, and so these values don't pertain to our definition of entropy, which is only defined by heat transfer for reversible processes. So what we have to do to calculate, sorry, I'm going to explicitly say that that's wrong. So what we have to do to calculate the change in entropy for the system in this case is we have to find a reversible path from the same initial to the same final state. And from that reversible path, then we can calculate what the equation is for the reversible heat transfer for that path. And from this value, we can calculate our delta S, or ds for the system. Luckily, in the problem that preceded this in your homework, it was exactly that. It was isothermal, reversible expansion from the same initial to the same final volume. And so you did this calculation in the earlier problem. I think the number ended up being 2.9 joules per Kelvin. Whatever it was definitely positive. So it's interesting to think for a moment about the fact that no energy flowed in or out of the system in the form of heat or work, and the internal energy didn't change at all for this initial or final state. Yet something important must have changed about this system. And we also might have an intuitive sense that that this final state is preferred over this initial state. And why is that? Okay, so there's this term that people call positional entropy, and let's do a slightly different but more visible example of positional entropy, which is analogous to gases expanding against vacuum. So here I've put, here I have a glass of water, and I'm going to put a drop of food coloring in, and I'm going to do this as carefully as I can because I want it to be all diffusion driven and no convection. I won't be able to limit convection entirely. I'm going to try to deposit this drop right at the bottom. Oops, without disturbing the liquid as much as possible. That was okay. So all of these ribbons and tendrils that you're seeing, those are all convection driven. But the blurriness that's beginning to emerge, that's diffusion driven. And in convection, there are viscous forces that are pulling and pushing, and that's not the analogy we want. What we want to think about is thinking about this diffusion analogy. So be focusing more on the blurring effect that's happening. All right. We know from our experience what we expect is in time for this dye to distribute throughout the water. And I did that experiment earlier just to make sure it happens. And indeed, here it is. Here's the dye distributed throughout the water. Now, if I asked, here I have this mixed up dye solution, and could you please keep an eye on it? So, actually, sorry, I'm going to back up. What is driving diffusion is random Brownian motion. So we have an image of molecules jostling and jiggling around on a random walk through the solution, and that image, that analogy is totally correct. So going back to here, if I asked you to keep an eye on this solution that has the dye completely diffused, and I said, watch it, and let me know if through all of this random jiggling, jostling motion, all of the dye molecules happen to end up clumped back together in a ball. I don't think you'd take me up on that job offer. you and I have probably never seen is diffusion dispersed dye spontaneously glom back together. And I'm guessing you could even explain to me why. So we might say something like, it would just be too unlikely for all of those randomly moving dye molecules to find themselves back in the same spot together. Unlikely and improbable are exactly the right words to say here. The entropy of this unmixed state is much lower than the entropy of this mixed state. And it only has to do with the position of the dye molecules relative to one another. So let's take this back. I'm going to try to leave this one here so we can watch it diffuse without disturbing it. So let's take this back to a diffusing gas. Let's consider a very compressed gas. And then we'll imagine that sometime later I move the piston and give these gas molecules access to a larger volume. So we'll call this time zero. So this is instantaneously later. I've moved the piston and the molecules haven't had time to diffuse yet. What we actually absolutely expect to happen in time, so I'll call this an instant later, but sometime after that, what we would expect is for these molecules to have diffused throughout the volume available to them. And it would be very surprising for us to come back to this piston sometime later and see something like these four molecules clumped back together. And you would have the same explanation as you did for the dye. It just seems so unlikely or so improbable that in the random motion of these molecules, they would align this way. The difference, the preference for this state, especially when we think about ideal gases, the preference for this state is not at all driven by energy. These guys aren't interacting. They don't really know that their neighbor's there. It is not at all driven by energy, but it is entirely probability and entropy driven.